Today is July 30th, 2015. The structure of sunspots. And for those that are interested in what I'm actually reading, I don't agree with Gamow's ideas of the Big Bang and all that nonsense, but A Star Called the Sun by George Gamow, and it's funny because it also says, author of A Planet Called Earth. Little does he know that the Earth is an ancient star, but here's a diagram that I pulled from that book. I don't know if you can see the diagram right there. It's on page 95. Now it has sunspots as being north and south, obviously. And you have three components to the sunspot with regards to the left-hand rule. You have your magnetic lines of flux. Remember, those are Draftsman's artifice. There are no actual lines wrapping around, going into the interior, and coming back out again. And this outer area is the photosphere of the sun. The electric currents are there, and, well, the force material will go into that in a little bit. Basically, sunspots are giant electromagnets. They're very, very, very strong magnetic fields that are produced where the sunspots are located. The calculations in the book doesn't really go over too much because it's for the public, for easy reading to understand. Is that the sunspots and the internal structure of them has them producing several thousand billion amps of juice. That's a lot of juice, okay? Flowing in concentric circles around where the magnetic field is located. Basically, it's a giant river of electrically charged matter. It creates these huge looping prominences that sometimes can be seen, sometimes are a bit invisible. And the charged particles are also field aligned. Now, to understand this, because I wanted to try to make it easy for myself to understand as well, you have the left-hand rule again. You have your middle finger acting as the direction of the electric current. You have the direction of the magnetic field as your index finger, and you have the force material as your thumb. So given we know 2 out of the 3, you can determine which way the force material will want to go. So you have the field alignment, so the magnetic field is going this direction. You have your current. The current wraps around the field at a 90-degree angle. And then you have the force material, meaning the material will be forced, electromagnetically forced, by the way, upwards. So literally, it will be forced up, out of the sunspot, and all the way back down into the other side. And also, it means that they're also field aligned. That too, well, if it's charged and there's a magnetic field in the vicinity, it will be field aligned, meaning it will align itself to wherever the magnetic field orientation is. Because that's, how plasma works. It goes wherever there's a strong magnetic field, and it aligns based off of wherever those magnetic fields are. So the charged field will go up and fall back down again because of the gravitational pull of the object. For a future talk, I want to go over turbulence, because I realized that I didn't include it in the main concepts paper, but turbulence in regards to, Reynolds number, I misspelled that, and, laminar flow and turbulent flow, how fluids can move through areas of, areas that produce turbulence. Fluids, based off of, the viscosity, how fast they're moving, how dense the fluids are. Because the sun, now I know there's a new theory out there saying it's a metallic liquid hydrogen, but I'm not too sure about that. I think the sun is comprised of plasma. It's very, very energetic ionized material. But anyways, if it's a plasma, then a lot of the turbulence should be factored into there based off of how the material is magnetically forced. Because the turbulence isn't like a regular liquid where you have a river flowing. Because if you hold a magnet next to, water, it's not going to do much. But if all that is a river of plasma and you hold a magnet to it, you can force that material to do really strange things and move in ways where you didn't expect it to move. And I think for the future, it would be wise, if we're going to send probes out to the sun, to figure out a way to have the probe, for instance, you have, your little probe. I'm just going to draw a box. That's a very crappy probe. But if you have it go towards the sun, what you can do is have a really, really strong magnetic field produced by the probe. I don't know how that would work, maybe with superconducting material. And as it gets closer to the sun, it will field line all the charged material. And then what that charged material can do is then power the probe. So literally, if we could figure out how to first have some type of magnetic field generation inside of the probe, and then have some type of feedback loop to where it will stop producing its magnetic field, and then the magnetic field will then be produced just by coursing through the solar interior. And we could probably get an incredible amount of data with that, and we could literally measure all these different layers of the sun and what all the elements are doing in there, and how much of an abundance they're there, and all that good stuff. But I don't know. I don't think that's going to be possible now, but I'm sure somebody's out there thinking about it. All right, everybody, take it easy.